Hello, let us continue our discussion of AMC 12 from year 2015, version B, number 25. So, until this point, we have been relying on the fact that if you multiply 12 to 30 degrees, that's equal to 360 degrees, thus we're guaranteed to have a lot of same directions, a lot of coterminal angles in the problem. The whole thing is periodic with period of 12 in terms of the J. Now, what if there's just one tiny change? Just one tiny change where that changes to 31. That one little difference totally changed the complexity of the whole problem. The periodicity is greatly expanded. It's now 31 times 360, which is more than 2015 that they gave us. You can no longer rely on periodicity to solve the problem. Is there no way to solve the problem? Actually, there is. Let's start by making this problem as general as possible. To make this thing as general as possible, let's change that 1 to k. That means this thing also has to be changed to k. Yeah, so it's actually starting a certain set distance already. And then you're adding 1 to that distance all the time. And change this angle to theta. And let us say that this is in radians. If it's not in radians, you can always convert the answer by having something in degrees be equal to pi over 180 theta d value radians. And I might as well highlight what is the units. Units is this guy, and unit here is radians, which is actually a dimensionless quantity. Yeah, so theta d degrees equals to pi times theta d divided by 180. Unit here is degrees, unit here is radians. So you can always change to that. Why? Well, let's look at the situation one more time. We have a beast that starts from here. It goes east, turns, goes a little bit more, turns, goes even more, and not such. Now, can we find a way to express this turning behavior? Let's think about our number line. You have all studied number line. Now, what is a number line? It's a straight line where all the numbers listed on there are real numbers. If you think about number line, that's a straight line, so only two directions. If you put any two directions within the number line, the angle between those directions are either 0 and 180 degrees. What if, for some reason, you had a point here and want to rotate something other than the 180 degrees? That is, here's your number line vector, and you want to rotate it in an angle that's something other than 180 degrees. If you draw a picture, let's say you do the 90 degrees, you're now pointing at direction totally away from you, the number line. But if you rotate 90 degrees more, you're again back to the number line, except you're pointing to -1. So what quantity where if you do it twice? And doing it twice, there's several ways to think about this. You could think about it as multiplying 2 to the 90 degrees, but you could also think about certain operation where if you square it, you get -1. What is that? That is the complex number I. One of the ways to understand complex number is not just the fact that it's an imaginary number, it also is a quantity that tells you how much potential it has of rotating a number vector in a certain degree. It's a potential for the rotation. You can think of I as rotating twice, rotating 90 degrees twice to arrive at this. So this one, you can think of this as not rotating 90 degrees, but rotating just a little bit. Find a complex number expression that tells you how you can do this kind of rotation. Is there such a complex expression? Actually, there is. So, this is the reason why some of you have learned trigonometric representation of complex number. Let's review that just a little bit. So if you have a number a plus bi, you can think of that as a quantity that has a in the real axis and b, I, in the imaginary axis. If you think about this point, that point is at a distance of a squared plus b squared, the whole thing square root, from the origin. And you can also think about it as having a reference angle rotation that is theta from the reference direction. As you probably are familiar with the trigonometry, unit circle representation, you are 0 degrees. Your reference direction is always to the right, the positive x direction. So this theta is just angle theta rotation from the positive reference direction. This theta value can be calculated. It is inverse tangent of b over a, and then you have this little n pi part where n is either 0 or 1. The reason is, if you remember from the trigonometry again, inverse of tangent can only give you a value that's between minus pi over 2, which is this direction, minus pi over 2 radians, to pi over 2 radians, which is totally up. If your complex number is in second or third quadrant, then if we just take an inverse tangent, you actually get a direction that's like this when b over a is negative. So if your a plus bi really is in fourth quadrant, then you don't need to do anything further. But if it's in second quadrant, we have to add pi, or add or subtract pi, whichever is easier. Usually adding a pi would be easier because you have a number that's negative, and by adding a pi, you have a number that's positive. And similarly, if you happen to have a complex number pointing to the third quadrant, then take the inverse tangent, that'll give you an angle in the first quadrant, add pi, you'll get the angle you need. So you could reanalyze this thing into a picture that looks like this, using polar coordinate like structure where you depict this point as at a point r theta. R is the distance from the origin. Theta is this reference direction that we just had. And then the corresponding a and b values are a equals to r cosine theta, and the I times b equals to I times r sine theta. Now, is there a nice little angle operation that you can do to show all this cosine and sine thing? There actually is. If you take an exponent of a complex number, so if you have purely imagined number, and if you take an exponent of that, you actually get this identity. Now, the proof of this will be very long, so I'll skip it. But I like to show you that this is behind the famous Euler's formula, where if you put pi where the theta is, then E of I pi equals to cosine of pi plus I times sine pi. Cosine of pi equals to -1. Sine pi equals 0, and 0 times I, even if it's I, what is the rotation of an object that's 0? If you have a point, no matter where you spin it, you're not going to go anywhere. So that's just equal to 0, so that whole thing is minus 1. So that leads to a rather famous equation. E to the I pi plus 1 equals 0, which is known as Euler's formula. Many people like this because it ties together many of the most fundamental constants in the mathematics together. There's 0, which is identity for the addition and subtraction. There is 1, which is identity for multiplication and division. There's the E, which is a number we need for growth. Pi, which is a number that's always involved in geometry. And I, the one that rotates it all. In fact, I, you can say, is a great connector. Just like I can connect something from a real number to another part of the real number. So, we could rewrite A plus BI equals to R times cosine theta plus I sine theta. Look here, A, R cosine theta, I sine theta. So, replace this part with E to the I theta. You can rewrite this as E to the log natural of R times E to the I theta. Using property of logarithm, we can rewrite this as E to the ln R plus I theta. Or another way to rewrite this is some number times E to the I theta, which I wrote as R, this angle thing theta. That angle thing theta in the previous lecture is this E to the I theta. So let's use this to solve the problem. Let's rewrite all the coordinates. P0 is just 0. It's our origin. P1, which is 1 unit to the east. And as you can see from there, 1 unit to the east can be thought as just 1 unit to the positive real direction. So just write 1. Instead of writing two brackets, as we need to do for x and y or vector rotation, we can just write P of 1 equals to 1 in the complex plane and be done with. P of 2, which was this point 1 plus 2 times cosine theta in terms of the x, and then I times 2 sine theta. So in the x and y coordinate, we used to wrote this as 1 plus 2 cosine theta, 2 sine theta. And in complex plane, instead of writing this parenthesis and the comma and 2 numbers, and even with the vectors, you either do this or you'll be writing as 1 plus 2 cosine theta, I hat, or x hat, whatever you like, plus 2 times sine theta, j hat, or y hat, whatever you like, write it like this. So in a way, this I is replacing a lot of things here. P of 3. Now it's getting tedious to write everything, so I'm going to write it as P of 2 plus 3 times cosine of, cosine of 2 theta plus I sine 2 theta, 3 times. Now, what should we do about that 2? Well, let's look at the Euler formula again. So, this one, we should be able to write this as e to the I 2 times theta, right? Well, we could think about this as e to the I theta squared. So, p to the 4, you can think of it as whatever p to the 3 is, plus 4 times e to the I theta cubed. If we start writing it like this, then we can actually say p to the n using summation as, let's see, I use k, I don't want to use ij, so let's use, I want to save n for something else. So let's say m equals to 1 to n, and then the summation is m times e to the I theta m minus 1. So we actually have something similar to an infinite, well, it's not infinite, something similar to geometric series, except this little m that's kind of bugging us. And also, I shouldn't have used 1 here. That thing was, since we generalize it, it's k. So that is k, and that is k plus 1. And here is k plus 2, k plus 3. So instead of putting m here, I should have rewritten this as k plus m minus 1 e to the I theta m minus 1. Let's see, 4 gets k plus 3, so 4. So if m is 4, 4 minus 1 is 3, 4 minus 1 is 3, okay, that makes sense. And then k always existed, so I can't do anything about this. So this is what we need to solve. How do we do such a problem? There is a couple of ways. So let us take advantage of the fact that whenever you have a summation, we could take out the parts that is, we could actually divide the whole thing where we have plus or minus sign. So we can rewrite p of n as summation of m equals to 1 to n k minus 1 times e to the I theta m minus 1 plus part that is more complicated. This one is actually easy. The reason why this one is easy is because we actually have an equation for this. So let's say that you have a typical geometric series g of n, where g of n is equal to g of 1, whatever the g of 1 value is, times the ratio r to the n minus 1 power. This is a typical geometric series equation. If this is the case, summation from n equals to 1 to, not n, I'm going to keep this, m equals to 1 to n, g of m is equal to g of 1, 1 minus r to the n, 1 minus r. You can see that this equation can be directly used here, where g of 1 is whatever we get if we put 1 in here, and k minus 1, well, we can't do anything about that. That just is k minus 1. And then this one, if you plug it in here, we get our r is being replaced by e to the I theta, so it is 1 minus e to the I n theta. Again, property exponent. Divide by 1 minus e to the I theta. Now, I do want to show you this part. because this let us handle the case where k is not equal to 1 in our problem. If k equals to 1, this portion, this sum, oh dear, let me rewrite this. I have to rewrite the g of 1 again. So our g of 1 equals to k minus 1, and then if you put 1 there, it's just as times 1. So our g of 1 is just k minus 1, and the summation will be this k minus 1, 1 minus e to the I n theta over 1 minus e to the I theta. Okay, yeah. That was what I was trying to, say here, because, yeah, e to the I 0, and that part is just equal to 1. And if you put k equals to 1, this whole thing disappears. If k is not equal to 1, all you have to do is calculate this and add it to the whatever guy you get. Now this e to the I theta, e to the I n theta, no matter what you do, e to the I n theta is just a cosine of n theta plus I sine of n theta. So this is a number, just a number if they give you theta in the end. A number between minus 1 to 1, and that also is just a number between minus 1 to 1. A single number. E to the I theta is also a single number. If you have everything that's just a single number only, then it's something that you can easily do by hand if you can properly calculate this guy. Now, I do know that for complicated data, and troublesome n value, we will need a calculator to do this, but it is not something that's impossible. So this part can be done easily. What about this part? Well, discussion of this part will take another good amount of time, so let's discuss this part in the next lecture.